Mr. Bergmann, is that a flute you're trying to play?
You know, it's not working. You know, I thought that I could actually play a flute, but it's not working.
You actually have to, like, do something other than, you know, hit it or hum or bang on it.
Oh,
hey,
hey,
you got sound. Hey. We're not quite, you know, not quite Jethro Tull yet. Or, yeah. Let's keep working on that one.
You know, I really need to work. You know,
yeah.
I was a great kazoo player, but the flute
I don't know about that.
You don't think so?
Well, yeah.
The flute is definitely a challenging instrument.
Yeah.
I'm going to have to kind of pass.
Why don't you keep going on that one? Yeah, take some lessons from your daughter.
Yeah, my daughter is much better at this than me.
Yeah, we got some interesting text problems going on
well,
here.
you can see this. We're going to talk about things called precipitation reactions, acid-base reactions, and several various and sundry other things.
At least you moved on to a woodwind, a legitimate instrument, versus, you know, kazoo or ukulele or bucket.
What's up with the ukulele? I think the ukulele is a
maybe if you had four strings on your ukulele instead of just 2.
That's true. That might be an issue.
Yeah,
I think so. Okay, today we're going to learn about reactions. We're going to learn how to predict reactions, like predicting the weather. It's like an art form, isn't it?
It is, very much so. And you really just kind of have to wrestle through them. You know, I've actually had students say, Mr. Sams, I thought you're the teacher. Shouldn't you know how to do this? When I look at a reaction I've never seen before, I'm going to wrestle through it the exact same way that you guys are. Now,
this text I know is small, so if you're looking at this on the small screen, it makes it kind of tough because, but look at the handout. It says, basically the goal is to predict products and chemical reactions, and we're going to learn how to do that today. But before we can do that, we have to learn about something called the
Macaluso
solubility rules.
Yes.
Now, in our classes, we expect you to memorize the solubility rules, but we don't do them in the standard way.
No.
We have something called the rules called the
Macaluso.
The Macalusos. Everybody say Macaluso.
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 Very good.
Macaluso. Now, what does Macaluso stand for, Mr. Sam?
Well, you've got the NAS.
NAS stand for the sodium compound.
You have the coals.
Stand for the chlorides. Actually, that should say Cl negative. Okay, the chlorides.
The NOs.
The nitrates.
And the SOs.
The sulfates. And the rest of them are the issue. Here's the situation here. The situation is that the sodium compounds are all soluble. Every single sodium compound is soluble. There are no exceptions down here. Now, when I say a sodium compound, when I say Na, I do not just mean sodium itself, although I do. I also mean any element that is a alkali metal.
Alkali metal, yeah.
Which include potassium, lithium, rubidium, cesium, and ammonium? Is that one of them alkali metals?
That is not an alkali metal, but it often behaves like one in terms of solubility.
So actually, you need to kind of think of ammonium as a Na in the Macaluso rule system.
Yep.
Okay?
By the way, one thing, we're talking about solubility in water, specifically.
Yes. This is aqueous solutions only.
Right.
So aqueous solution, this applies only to there. Then, of course, the coals. Now, the rule is that all coals are...
they're all soluble.
With a few notable exceptions.
Yeah.
What are the exceptions?
Well, we got silver chloride, mercury 1 chloride.
Now, how would you write the formula of mercury 1 chloride, Mr. Sams?
I would write Hg2Cl2 because mercury 1 ions are diatomic. They're really weird, but they always go in pairs.
And, of course, the lead 2 chloride.
Yes, lead 2 chloride.
Now, this does not just include chlorides.
Nope, it's all the halogens because everybody in the same family has really similar properties.
Look at your periodic table. If you don't have it out, you may want to pull it out. You can probably use it here today anyways. So if you look at your periodic table, the halogens, of course, are the second to last column right next to the noble gases on the periodic table.
Yep.
And so chloride is one of them in there. Fluoride's at the top of the list, but the naphthalnosos didn't sound right, so we called them Nacolnosos.
There you go.
That moves us.
Mr. Bergmann is having a coughing fit here. Next, we're going to move on to the NOs. And the NOs are nitrates. And all nitrates are always soluble. If you ever see nitrate, there are no exceptions to its solubility.
No, they are all soluble.
Very soluble.
That also includes
chlorate and acetate.
If you see an acetate or a chlorate, it will always be soluble, no exceptions.
Correct.
And lastly, we get the SOs, and that, of course, stands for the sulfates. And there are no other kind of family members here. So it's just the sulfates. Now, all sulfates are soluble. Except for
barium sulfate, calcium sulfate, lead 2 sulfate, and mercury 2 sulfate.
That means these are the things. What this is, the Nacolnosos are the things that are soluble, the ones that dissolve in water.
Yes.
They are the soluble compounds. The rest are not soluble or insoluble.
Yep.
That includes sulfites, carbonates, chromates, phosphates, phosphites, oxides, and hydroxides. Now,
and so on
and so forth.
There are others.
Now, we do need to talk about, this is hard to see down here. Again, we have some issues. But if that's the case, let's just talk about the hydroxides, just real quickly. At least the alkaline earth metal hydroxides. What would you do with barium hydroxide? Is that soluble, Mr. Sams?
Well, that's usually classified as something called slightly soluble.
We have sort of a weird category here, folks. It's called the slightly solubles, and that would be the alkaline earth metal hydroxides.
Right. Magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. So these guys, the deal with them is that you can dissolve some of them in water a little bit, so they will make a solution, but if you ever produce them as a product, it's going to form a precipitate.
So this is a little bit confusing because technically solubility, we haven't really talked about this yet, but we will as time goes on. Solubility is actually a number, and so at what number do you, everything is actually soluble to some degree, but some are so insoluble it's hard to even talk about them that way. But everything has some slight degree of solubility, so at what value do you say it's soluble versus insoluble? And these are ones that are kind of like on the border.
Yeah.
Okay, so that's easier to do. Now, we say all things are soluble back here. Let me jump back to the screen, Mr. Sams. If I say that these things are not soluble, like sulfide, okay, if sulfide's not soluble, what would you do with, say, sodium sulfide? Would that be soluble?
Well, since it is a sodium compound, I think the solubility of the sodium supersedes the insolubility of the sulfide.
Yeah, so one thing I wanted to say about these rules that's important to note is that the Macalusos trump the not-solubles.
Yep.
So if something is a sodium compound, even if it is one of these non-soluble compounds, like sodium chromate or potassium chromate or something like that, these trump. So Macalusos, these trump the other ones.
Yep.
And that's something that helps you understand that.
Yeah, so the deal is look for the Macalusos first.
Yes, indeed.
And then assume not soluble if it's not on the list.
Indeed. Very good, Mr. Sams. Now, this particular podcast has lots of text. And frankly, to read this on a small screen might be a tough thing. But we're just going to talk you through how we do these
Ionic and net ionic equations.
Yeah, ionic and ionic equations. But you should follow along in your text.
Yeah, look at the
handouts. If you're watching on this on the internet, you're going to want to have access to these texts. All right, so we
email us. We'll give it to you.
Well, yeah, certainly, or we might put a packet together. Okay, so how do we write ionic and net ionic equations? I think I'm going to go to the old black screen here, or white screen, I guess it is.
Yep, that's going to be easier to read.
What we want to do is if we've got a reaction, like we've got the cadmium nitrate here, and we react it with the sodium sulfide.
A little 2 after your nitrate there.
Oh, I needed 2, thank you. And these are both aqueous, and how do you know those are aqueous, by the way, Mr. Sams?
Well, we have a nitrate, which are always soluble, and we have a sodium, which is always soluble. So we have a Na and a No.
And how do I know that's a precipitate, CDS?
Well, that's a sulfide, and all sulfides are insoluble unless they have a Na with them.
So yeah, so we have a No here, a Na here, and the cadmium is neither, and we have a nano, and nanos.
Nanos are way soluble.
Very soluble. So this is the substance that's insoluble. And so basically this is called the complete reaction. It does need to be balanced, so I'd have to put a 2 in front of the sodium nitrate. Yep. I believe is all I have to do.
That'll do it.
That's the regular reaction. I'm just copying this down. I think it's good to kind of see me walk through this process.
Yeah.
If I want to then write the ionic equation, you see when something gets dropped into water that's soluble, what happens to it, at least an ionic compound?
Well, in the last podcast, we learned that it dissociates and it splits up into its individual ions.
So I'm going to split that up into 2 individual ions, this cadmium and the nitrate. Now, I do have to put a 2 here. Why do I have to put a 2 there, Mr. Sams?
Well, you had 2 of them in the compound, indicated by that little 2 outside the parentheses, and when it splits up, we need to indicate that with a 2 coefficient, stating that there's 2 nitrates floating around in solution.
Because sodium sulfide is also one of these.
Yep.
I must split it apart. It's a Na. And you see, essentially, if you were to look inside of a beaker, I'll jump back to this in just a moment. If I were to look inside of a beaker of this solution, right before kind of everything happened, you would find sodium ions, you'd find sulfide ions, you'd find cadmium ions, cadmium 2 positive ions, and nitrate ions.
Now that's one little thing. One thing I've always told my students is stick your head in the beaker. Don't literally stick your head in the beaker, obviously, but pretend you got this tiny little scuba suit, and you shrink down really, really tiny, and you jump into the beaker. What are you going to see floating around in there? Because that is the key to all solution chemistry. Get in there, see what's in there, and what's going to react with what.
And so you have sulfide, cadmium, and the nitrate. Who's going to get together? And of course, this is kind of part of prediction, and we're not really doing that just yet. But we know it's going to make this CDS. Now, I leave this together. Now, why in the world would I do that, Mr. Sams?
Well, it forms a solid, meaning it's not in an aqueous solution, so we're going to have to keep it together. It's a precipitate.
Yeah, and I think of them as they're sticky. They like each other.
Yep.
Precipitates or insoluble things are sticky. They like to stick together, and so that's what it makes. This is called the Ionic Equation. This is actually kind of what goes on. So we kind of go back to our beaker, and you got the little guy swimming around. There's his flippers. Okay, is the cadmium sees the sulfide and says, "Hooda, hooda, hooda, you are a good-looking chick," or whatever, and the cadmium gets together with the sulfide because they like each other. Now, sodium sees nitrate and says, "Nah, nah, nah, nah." Ooh, you're good. I played the flute for that one, but I don't think I could actually make a sound. And then lastly, if I want to make what we call the net ionic equation. You ever been to a game, Mr. Sams, like a football game?
Occasionally, yeah.
And when you go to a football game, what are you typically, what is your role?
I am a spectator. Yes. I am not by any means an athlete.
At the dance is the cadmium met the sulfide right here, and they made cadmium sulfide. So that's like the action that happened at the game.
Yep.
Well, who was sitting around watching?
Nitrate. Didn't do anything.
See, he's the same on both sides of this reaction, so he's called the spectator ion.
Sat around and watched cadmium and sulfide join up.
And then the sodiums also did the same.
Yep.
So the net ionic reaction is just sort of what happened, what was the action. I'm not going to write the AQ here because chemists don't like to do that. If they don't have to, it's a bit of a lazy thing. And that's the answer. We will put a solid here. That is called the net ionic reaction.
Yep. Net is what is left over after all the other stuff happens.
Indeed. Okay, now we want to talk about how we can predict products in a reaction. Now, we've divided our reactions into redox reactions and non-redox reactions. And so today we're only going to look at the
non-redox.
The right side of this chart on the it says reaction. If you look at this part, it says reaction. It's got two big halves. Well, we're only going to look at the right side. Later on we'll look at the left. And so these are essentially the rules. How do you know if you have a non-redox? Now, we don't know what redox is yet, but we're going to learn about that very soon. It's two ionic compounds, like your typical double replacement reactions that you learned in a first-year chemistry class. If you see an oxide, then you know you have a double, or you have a non-redox reaction. Acid-base reactions are all non-redox. Decomposition reactions are usually non-redox. There are some exceptions. If you see a word like equimolar, it's most likely an acid-base reactions. If you see protic or diprotic, that is also. And there's this funny thing called a coordination compound. We're going to have to talk ourselves through that and do some examples. So these are just kind of this is just a big schematic that's going to help you as you solve these problems. And
I mean, we could go through and beat those rules to death, but frankly, guys, you're going to learn more about this by doing it than you are by sitting and listening to us do this.
So we're going to just probably do lots of examples. And there is lots of text now that says types of reactions, and I have it printed here. And you feel free to knock yourself out and read all this stuff. But these next few slides are all right here. I think I will talk a little bit about oxides. So let's turn to the oxides. Roman numeral 1 is probably not terribly important, but Roman numeral 2 is.
Yes, very much so.
So if I have a oxide, there are two varieties of oxides. Mr. Sams, what are those two varieties?
We got non-metal oxides and we have metal oxides.
So let's do non-metal oxides first. If I had a non-metal oxide, that would be, for example, a non-metal. Give me an example of a non-metal, Mr. Sams.
Sulfur.
Sulfur. Now, that's where do you find that on the periodic table?
That is to the right of our little stair-steppy guy over
like
there.
Sulfur dioxide.
There you go.
And when they react with water, primarily we look at them as water, they are going to turn into a non-metal oxides plus water always makes
an acid.
So we need to make an acid that has hydrogen. Of course, acids have hydrogen in it. And then, of course, sulfur and oxygen. So you've got H, S, and O. So you have to kind of figure out what the formula is going to be. These are like very, very easy. I like to just say add them together.
Yeah, you pretty much just smush them together, and most of them work that way. The sulfur ones work, for sure.
H2SO3.
H2SO3.
That is the answer. I've predicted that if I take a non-metal oxide, sulfur dioxide, put water, it works. Or if I take, say, carbon dioxide, another non-metal oxide, add to water, you would do the same ball game. Instead of S, you have H2CO3, carbonic acid. Now, what about this one, sulfur trioxide? That's a little trickier. What's that going to make?
I see H2.